General relativity, step by step. Last time we talked about transformation of basis vectors from one system to another. EI equals this. And we've got this system where it's summed over the blue indices. Have I got my cursor? Is that there? Is that there? Yeah. We're summing over the blue indices, and the red index was common to both. That I there equals that I there, but it's summed over the j's. So what I'm going to do is I'm going to consider vectors of a particular type. I'm going to consider gradients of a scalar, or the gradient vector. And in vector calculus you write it grad f, where f equals f of, let's just say, x, y, z. Well, actually I'm just going to consider two dimensions so I can draw it for the moment. There it is, f of x, y. And this might be temperature. Oops, temperature. So you've got this nice sort of square little thing here. You've got an x coordinate and a y coordinate, and you've got contours of temperature. So there's a hot spot there, there might be another hot spot here, and you've got coordinates floating around like that. So these are contours of equal f. And of course what we want is the gradient of this, which we're going to call grad f, and the gradient of that is grad f, which is di f di x comma di f di y. That's a row vector. I'm going to put a t there to make it a column vector for reasons that will become apparent. Now, this notation here is a little bit peculiar. I'm going to call it G. So G1 equals di f di x1, and G2 equals di f di x2. So x1 is the same as x, and x2 is the same as y. But you can imagine I can carry on. Gn equals di f by di xn. So it's a nice little system here. So I can say that Gi equals di f di xi. And I might ask, what is grad f when expressed in a different coordinate system? In a coordinate system with bars. So here we had x1, x2 up to xn. Now I've got x bar 1, x bar 2 up to x bar n. And so my gradient in the barred system, 1, equals di f by di x bar 1. And then g bar 2 equals di f by di x bar 2, and so on, all the way up to g bar n, which equals di f by di x bar n. So I want a relationship. I want to change, or to express, Gi in terms of Gi bar. I want to be able to convert between these two systems here. Well, let's have a look at it. Well, let's see what let's see what happens. What is di f by di xi? Well, that of course is equal to Gi, and that equals di f di x bar 1 di x bar 1 di xi plus di f di x bar 2 di x bar 2 di xi plus ... all the way through to di f di x bar n di x bar n di xi. Expressing the fact that f changes. F is a function of the barred system and the unbarred system. So I've got f equals f of x1, x2 up to xn, but I can also express it in terms of x bar 1, x bar 2, dot dot dot, x bar n. And you remember from that h theta business that the two systems can intertwine and interrelate in complicated ways. So let me just go through this again. Let me just write it out. That's gi equals di f by di x1 bar, di x bar 1 di xi, plus dot dot dot, plus di f di x bar n di x bar n di xi equals the sum from j equals 1 to n of di f di x bar j di x bar j di xi. And here's the killer. This thing is by definition g bar j. Okay? Because it is the rate of change of f with respect to the barred coordinates. So now I can say that gi equals sigma j equals 1 to n of gj bar di x bar j by di xi. Now I can use colour coding. I can get rid of this, no, it's this one. I can get rid of that I there and write it in blue, let's just say. I, and I can colour code my j into being red. There it is. J, and make this j as well. J, and that's red as well, I guess. Let's just make that red. J equals 1 to n. So we can see here that if I go back, let's go back quite a long way. This rule here, I wish I could cut and paste on Notepad, but I don't seem to be able to do that. This thing here, it's the same. I'm going to copy that down. I'm going to copy this basis vector transformation rule. I'll go back to black. EI basis vector equals sigma over j ej bar di x bar j by di xi. And I'll pinch in on that. That's not the neatest writing I've ever seen in my life. X bar j. And that's EJ vectors. So you can see how it's the same thing. Everything just goes across. Everything's the same thing. All I've done is replaced the G's with the E's and the G bars with the E bars. So it looks to be that these GI's, those components here, it looks to me like these, I say these because it's understood that I equals 1, 2, 3 up to n. These are components of a vector. That's equal to the gradient. And they transform in the same way as basis vectors. Because they've got the same transformation law. Now that might not look super surprising, and the way I've set it up it's kind of a, well, it's obvious mode. Until you see a type of vector which doesn't transform the same way, and this is the insight that we need. So I'm just going to stop there. I'm just going to say it again. The gradient vector, the components of a gradient that's G1, G2 up to Gm, transform into the components of a gradient with respect to a barred coordinate system. They transform into the components of a gradient in the same way as the coordinate bases do. And that might not sound like a very amazing thing. Well, that's what I want to get across to you. It's not amazing. Well, it's kind of amazing. It's kind of obvious the way I've set it up, but hopefully in the next one it won't be quite so obvious, because I'm going to talk about a different type of vector which transforms in a different way, and you'll see why this is so important. I'm going to stop here.